to the second Subsurface Systems Modeling webinar in 2025. As you know, the EAGE has a bunch of technical communities, and one of them is the Basin and Petroleum Systems Analysis Group. And this group is organizing this Subsurface Systems Modeling webinar. And in April, we gave an introduction. And today we have our, let's say, first real presentation. If you want to join the community, or let's say the EAGE, there's a QR code in the lower right corner. And so yeah, as I said, we started in April with a series, and we have already several confirmed speakers. And you can see here the outline. Today we start with Nicolaj Mahlstedt, and then we have some geothermal contributions, then some traditional basin modeling, and other topics. So the idea is that we cover not only oil and gas, but also lower carbon topics like geothermal, CCUS, and mineral systems and things like that. So if you're interested in keeping up with the schedule and also looking where we put the recordings and information from old and or past and future sessions, then go to this QR code displayed here in the upper right, and you will find more information. If you want to contribute, then feel free to contact either me, my name is Friedemann Bauer, or Maria Poller-Borges from the EAGE. So yeah, today I'm happy to welcome Nicolaj Mahlstedt. He is the senior technical officer at Geosphere. Geosphere is a company, I think, introduced by Brian Horsfield, and I think he is participating here as well today, specialized on kinetics. And yeah, Nicolaj has 15 years experience in upstream research and development. His focus is obviously on kinetics. He has published a lot of good papers, and he is supported by Alexander Hartwig here today. I think Alex will not present, but he will help answering questions or is present if anything arises. So with that, maybe just we will record the session. So actually, I should push the button right now. Oh, it is already. Perfect. So we will record the session. If you have any, let's say, short questions, just clarifying questions, I think Nick is okay. Maybe you could either raise your hand or write a question in the Q&A chat box. And then for the bigger questions, maybe we can hold them back towards the end of the presentation. I hope I didn't forget anything. So with that, Nick, the floor is yours.
All right. Hello. So I try to share my screen. It takes an hour max. Okay. Here. You see that, I guess?
Yes, correct.
Yes.
Okay. All right. Thanks a lot. So I'm going to present today about kinetics of liquids to late gas generation and prediction of bulk petroleum properties. So here at the beginning, directly the outline of the talk and some take-home messages. So bulk petroleum fluid prediction is a fundamentally important part of risk reduction. And we do that with a phase kinetics model that has delivered sound prediction for conventional plays for over 15 years now. I'm going to present this model with a few cases, examples, and also presenting some changes we introduced over the years. For example, using instantaneous compositions for populating the compositional kinetic models. Then I will also present our so-called Gore-Fed kinetics model, which combines those phase kinetics with secondary gas generation kinetics from in-source oil cracking and cracking of over-mature late gas into one more simple model, which strongly improves the fluid property prediction, especially for high maturity plays. I'm also going to shortly present that kinetic model for humic sources, so coal and coal shales, by using continuous maturity series to really construct a better kinetic model, as coals are known to not to undergo stabilizing reaction during maturation. So the least mature sample cannot be used for petroleum system modeling. And in the end, I would like to stress that all of those kinetic schemes are also usable on oil ascertains, which is pretty important in cases you do not have a source rock at hand, is missing, or you even do not know what the source rock is. So, okay, and all of those models I will were applied in a recent project that Alex Hartbeck, who's here and able to answer questions, presented at this year's EAGE annual, assessing the migration efficiency in the North Sea, mainly by comparing our models to predictions done using the default Pepper and Corvey kinetics. And yeah, the main outcome of this project was that both kinetic types, so our individual kinetics and Pepper and Corvey kinetics, perform equally well in terms of calculated numbers that were generated. But our individual drop and heather kinetics, for those, it spares of the considerable tuning that is needed to match the regional hydrogen carbon phase and GR ranges using the Pepper and Corvey default kinetics. So, okay, I would like to start with this slide. So predicting petroleum composition actually pervades the whole of the risking strategy. So clearly the presence and properties of source rock, seal, reservoir, trap are important geological controls, but density or viscosity and wettability of phase state are important chemical controls, petroleum property controls that actually define the extent of leakage or the producibility or the charge volume in our petroleum system. So those petroleum properties are actually a function of the chemical composition, which are in turn mainly related to primary source controls like kerogen type or the maturity, upon which secondary mainly physical controls act in the carrier reservoir system. So the petroleum system examples exist within this ternary diagram. For example, nicely controlled by maturity is the Zona de Campeche in offshore Mexico, where you see that gas-oil ratio, so GOR of the oil fields, increase drastically or increase from going from northeast to southwest, which is directly correlated to the underlying Thethonian source rocks here in blue, where you see the well noted with the vitronitrophlagms going from 0.5 to 1.3 in the northeast southwest direction. So this is a vertically charged system. Physically controlled are the gas and oil fields found in the Vikinggraben, Norway, meaning that mainly phase separation acted upon those fluid composition during upwards migration. So the fields plot all along, fall all along those calculated bubble and dew point curves in this GOR versus saturation pressure diagram, and converge roughly in the area where the Waller and Lille-Frick GORs are. So as Waller and Lille-Frick are undersaturated with respect to reservoir pressure, they can be sought to contain the initial fluid type present before phase separation evolution took place during pressure release and temperature release during upwards migration. Here, I would like to show that those bubble and dew point curves do not fall always in the same position and are rather characteristic for each petroleum system under investigations. So it can be easily seen here that for any given gas-liquid ratio, possible saturation pressures can differ as much equivalent to a range in depth of 2 kilometers. So this difference in saturation pressures in turn is again defined by the chemical composition of the fluids, which are initially defined by the initial composition of the kerogen, so type, so the macromolecular precursor of the petroleum. So what I would like to say is that the key to predict actually petroleum physical properties in a bottom-up approach is to determine the bulk composition of the petroleum that is first formed in the source rock as a function of maturity. So we do that with geosphere since years using an approach. What was there a question? Okay.
No,
so we do
fine.
this what? Sorry, I'm
no,
hearing
you
some.
can go on.
Okay, everything good. So we do this in a phase kinetics, an approach, a forward modeling approach called phase kinetics, which actually compares hydrocarbons generated in the lab to hydrocarbons generated under natural conditions in the carrier reservoir system. It utilizes, it consists of in 4 steps, utilizing open and closed system pyrolysis approaches, and to determine the petroleum type, the thermal response or kinetics, and the evolving composition of the generated fluids generated as a function of maturity. The gathered data can then be tuned in the final step into a PVT compatible format, and physical properties can be predicted. So I would like to run you through this to this model in the next 5 slides or so. So the first step consists in defining the petroleum type organophases by using open system pyrolysis GC, and from which we can infer petroleum type. Using this ternary diagram, which features long chain alkanes versus intermediate chain alkanes versus total gas. So the position of the pyrolysates in this ternary diagram roughly correlates to the GOR of the petroleum generated from the individual source rocks. And you can see at first sight that these can be very different compared to the initial classical kerogen types 1 through 3, and very different compared to the HI classification. And so, for example, terrigenous type 3 coals or coaly shales generate fluids that can be all from gas condensates to waxy oils, and we have recently shown for small petroleum system in the Barito Basin in southern Borneo, that Eocene coals are in fact or indeed the source for the waxy Tanjung oil family found in the system. So here the message is use individual samples to characterize your petroleum system. So in the second step, we run open system bulk pyrolysis at 3 different heating rates to determine the thermal response of the kerogen. So the stability of the different chemical bonds can be described by kinetic parameters, and we usually use a distribution of activation energies in a single frequency factor. So using a single frequency factor leads to activation energies characterizing so low activation energies characterize weak bonds and are stripped away during early charge or early conversion of the source rock, and high activation energy correspond to strong bonds and are stripped away later upon kerogen to petroleum conversion. So the main message here should also be that please use individual source rocks, because there is no rule of thumb and the kinetics depend strongly on organophases. For example, sulfur-rich source rocks are much less stable than sulfur-poor source rocks and generate much earlier upon thermal maturation. So now in the third step, the evolving compositions are determined by using closed system MSV pyrolysis run to increasing kerogen transformation ratios determined during open system pyrolysis. So the gathered closed system data, like a single gas species and liquid compounds, are tuned into a PVT compatible format, and then the final compositional kinetic models are so the open system kinetic potentials are populated by the closed pyrolysis compositional data. So like 10 years ago or so, we noticed that it is extremely important to actually populate those potentials with instantaneous composition generated between each transformation ratio, and not using the actually measured cumulative compositions. Because using those cumulative composition would lead to prediction of much too low GOR ratios. This is exemplified in this small sketch here, so showing a simple activation energy distribution just consisting of two potentials, which account for 50% of the bulk reaction. So thermal stress would lead to the realization of those potentials and to a cumulative yield curve like this. Now running MSV pyrolysis to 50 and 100% transformation would lead to cumulative compositions at the first step, for example, a GOR of 0.33, and at the 100% transformation to a GOR of 1.0. Now, for populating now the kinetic models, we have to use the instantaneous composition, meaning we populate the first potential with the cumulative composition because there's no lower transformation potential, but the second 50% potential has to be populated by higher GORs. So 3 gas units and only 1 oil unit, because that is actually the difference between this cumulative composition and that cumulative composition. Now, for full conversion in the kinetic model, this would again lead to a GOR of 1.0. Using cumulative compositions, so a GOR of 0.33 or 1.0 at the second potential would lead to, at full conversion, only to a GOR of 0.6. So that would mean that, so for the full phase kinetics model, the effect is the following. So if the instantaneous modeled composition follow nicely the MSSV cumulative directly measured yields, whereas the cumulative modeled compositions generate much too low GORs. So to drive this point, especially at high transformation ratios where we would expect higher GOR ratios to occur. So to drive this point home, the activation energy distribution needs to be populated with instantaneous compositions to predict cumulative fluid compositions. To use phase kinetic models, I would like to, and not default GOR kinetics, is important, as I would like to point out in this slide, where a selection of typical type B source rocks, phase kinetic predicted GORs are shown as a function of increasing thermal stress or at depths where those fluids were generated. So interestingly, all of those many marine source rocks show GORs which are much higher or which plot outside of the actual type B pepper and corvi organophaseous fields at maturities at similar maturity levels. So that means that a marine source rock at immature stages generates higher GORs than would be expected using a pepper and corvi type B default kinetics. So this has also an impact in the real world, which I would like to point out here. For a Draupner formation sourced undersaturated Madame Fell oil from the mid-North Sea, for which fetch area modeling indicates that it contains early mature oil charged at roughly 20% transformation ratio of the kerogen. So now using all the phase kinetics of our Draupner formation sample predicts exactly the same saturation. Now, GORs at reservoir pressure and also at saturation pressure. So which can also be for transformation ratio stages between 10 and 30%. So this can also be expressed in those phase envelopes, and where we see that those physical properties, where we see that the phase kinetics predict fluids in blue possess very similar compositions than the Madame Fell fluid compositions in yellow. So yes, this Madame Fell example was used in the aforementioned study from Alex Hartweg, and was mainly used or was used here to choose the correct or most representative Draupner formation sample for modeling, and also for calibrating the pepper and corvi kinetics. Because in this setting, the known source rocks were are typical type B Draupner and Heather formation source rocks, but using only the pepper and corvi kinetics showed that the B phases kinetics is often too labile, as shown before, and too oily, as shown before, so too low GORs. So for a correct matching using pepper and corvi kinetics, terrigenous type DE phases had to admixed to the type B source rock phases. So comparison of the ultimate expulsion potential for pepper and corvi phases are shown here, and for our GORFET models are shown here. And it's interesting to see that the Draupner kinetics generates the same composition as the B type organophases, and the Heather kinetics generates pretty similar compositions to the DE terrigenous organophases. Now, using the Draupner and the Heather GORFET models, which I will explain in a little while, changes the compositions to being more gas rich, as in those compositions we take care of high maturity secondary cracked oil, in-source oil cracking, and also of late gas generation, which might occur which occurs in the upper Viking Graben area. So here on the left-hand side, the modeled results are shown using those GORFET models, those individual GORFET models, and for the different reservoirs, really nicely leading to filling of the different structures and the oil and gas distributions are more or less correct. In terms of numbers, both models, so the GORFET and the Pepper and Corby mixed tuned model, perform equally well, and generally generating higher numbers than actually being discovered in the mid North Sea. So the reservoir here is a limiting factor. So if you have more questions to this topic, you can perfectly ask Alex, who is sitting around here. Okay, now I would like to come to how we constructed the GORFET model, which was used in those studies. So by beginning, so the GORFET model combines the secondary cracking schemes, in-source cracking schemes into the phase kinetics approach. So for assessing secondary cracking, it's also important to do that on an individual basis, because here also there's no rule of thumb. And as can be shown here, for example, high wax oils being cracked at secondarily cracked much higher temperatures than PNA oils. And even averaged or default kinetics shown here for PNA oils in the open diamonds can induce errors up to 10%, 10 degree in under basin conditions. So what we do to assess primary and we assess primary and secondary cracking kinetics in an approach called GORFET, which is very quick, which is quickly done actually. And the main trick here is to use open system biokinetic curves as spline functions that are fitted to the closed system MSSV data. Here all the dots, by using factors, or individual factors for the petroleum system derived from a single open pyrolysis GOR composition. So the spline curves can be fitted to the different datas, to primary oil and gas cracking data and to secondary cracking data. And doing that for 3 different heating rates, we can determine the kinetic parameters for primary for all the kinetics, for the liquid kinetics and the primary and secondary gas cracking kinetics. Another thermogenic gas, secondary thermogenic gas input we take care of in the GORFET model is the late gas potential, or the late methane generated at very high, from a matured organic matter and stabilized organic matter formed during maturation. So here we see MSSV, or closed system pyrolysis, measured late gas potential, which increase during catagenesis up to 2% vitronitrophlens to values between 40 and 50 milligram per gram TOC for many source rock, for all of the source rock types actually, and then decrease through catagenesis up to 3.5% vitronitrophlens. So this late gas generation can be predicted using a single frequency factor, single activation energy with a very low frequency factor, probably for each kerogen type, likely for each kerogen type, and stands for one fundamental, one single, or one specific reaction mechanism, namely the final demethylation of aromatic organic matter aromatized organic matter involving second order recombination or condensation reactions. So just as a small aside, the dependency of those primary and secondary kinetics on the organic matter type really decrease with increasing decrease with increasing decrease with increasing maturity. So for instance, for the late methane generation, this is fixed and not really dependent on the original organic matter type, which is also true for example, molecular hydrogen generation at very high temperatures. A topic, or the kinetics for that, was published roughly 3 years ago by us. And if you're interested in this hydrogen topic, you can also assess a talk I did give in the EAGE TSOP seminar last year in October. Alex will also talk about I think in his talk here in this webinar, about the hydrogen kinetics and how you model that. But for the GORFET model, the hydrogen is not needed, so that is not integrated in our GORFET model. So let's just continue with how we constructed now the GORFET model using the Draupner sample. So in the first step, we just ran GORFET to define the secondary gas kinetics for the Draupner sample, and use extrapolation to geological heating rates. Now, in the second step, we use the fixed frequency factor of the major bulk reaction from the Draupner formation, and to recalculate the secondary gas and late gas activation energy distributions, because we want to combine the model into one model, all the different kinetic parameters. So extrapolation to geological heating rates now gives us a very bad fit to the original data. So we can tune and shift this activation energy and manually fine-tune the recalculated activation energy distributions to best fit the original predictions. So for secondary gas, the activation energies have to be shifted each one activation energy higher, and for late gas, the activation energies have to be shifted each minus 9 activation energies lower. So now we can actually already put together the GORFET kinetic model by finding normalization factors for each of the kinetics. So those can be directly derived from the GORFET stoichiometrics. Only for secondary gas, we have to determine actually the expulsion efficiency to assess how much is retained in the source rock usually and available for secondary cracking. So for the Draupner formation as a good expeller, expulsion efficiency can be assumed to range around 85%. So only 15% is retained in the source and can be cracked at later stages. So therefore, the activation energies potential for the secondary gas stage are rather low in this example, and having the effect on the generation and transformation rate curves that the stabilized GORFET bulk kinetic is so the stabilization occurs very late and is mainly related to the late gas charge for the sample. This is a little bit different for example, the Heather GORFET model, because the Heather formation is a worse expeller and perhaps with an assumed expulsion efficiency of 70%. So 30% are retained, and the secondary gas potentials take a more important role in the model, and leading to deviation of the GORFET model from the original biokinetic models at earlier temperatures, and leading to much higher GORs during maturation and modeling. So in the final step, we can also populate those or build compositional kinetic models as for phase kinetics using the GORFIT closed system MSSV data. So in the study of Alex, he used the two compounds kinetics or oil and gas kinetic model for modeling. I would like to announce that he will also present those results at the Petroleum Systems Conference in Oslo in September, but this time for yet to find study extended to other areas on the Norwegian continental shelf where coals play a much more important role as source rocks. So this brings me actually to the third topic, or the necessity to build combined kinetics for humic sources using continuous maturity series sample. So this approach is needed because lignocellulosic organic matter in coals or type 3 humic coals during maturation not only generates petroleum products by beta cleavage like seen for more lipidic organic matter in marine shales, but here maturation proceeds over aromatization and condensation reactions leading to a rearrangement and stabilization of the organic matter. So that has the effect that more mature samples, or the generation rate curve of more mature samples, step out of the generation rate curves of the less mature samples. So that causing the problem that the least mature sample of the series is not suitable for petroleum system modeling. So to overcome this problem, we combined the transformation ratio rate curves, or the TOC normalized transformation ratio rate curve of this German coals maturity series in a way that we stepwise build a combined curve by allowing each transformation ratio rate curve to be only valid up to the maturity level of the sample. So having gathered this combined curve, we can see that the combined curve, or the hydrogen index, or the cumulative transformation ratio, is much lower than that of the least mature sample, which tells us really that natural petroleum generation proceeds via aromatization and condensation reactions, leading to the neoformation of dead carbon. We also did that, built a combined kinetics model for aura formation, for a small aura formation maturity series. And here the cumulative yields for the combined curve in pink is not much lower than that of the least mature sample. So here for the aura formation of the P&A Lowex producing aura formation coals, the petroleum generation proceeds via aromatization and condensation reaction, but also via normal sidechain cracking, leading to the neoformation of only low dead carbon contents. Importantly, here what we also did is, for this combined model, we used we also did run GORFIT analysis and constructed an aura and GORFET model that was directly applied for phase for prediction for the Noatun gas and condensate field in mid-Norway on the southern Halten terrace. In this area, upper Jurassic source rocks are ruled out due to structural configuration, and the fetch area modeling indicates that the Noatun gas fields contains mature gas and condensates, or corresponding to roughly 80% transformation ratio of kerogen transformation ratio. So using this ore formation gore-fed kinetics shows us that it fits perfectly with the GOR values for the Northern gas fields at transformation ratio of between 80 and 85. So this is for the instantaneous composition. So this Northern gas condensates seem to contain instantaneously generated high mature fluids from the ore formation. This can be also expressed in those phase envelopes, which are almost identical for the gore-fed predicted fluids and for the Norton fluids. Okay, this brings me to the last topic. That is that all of those kinetic approaches can be used on oil asphaltenes, as exemplified in those phase envelopes for comparing a Draupner formation kerogen to a respective Tarmat asphaltene and a Duvernay formation kerogen to a reservoir oil asphaltene. So they show very similar envelopes, meaning that similar physical properties of the fluids can be, or that the fluids have similar properties, and so reservoir asphaltenes can be used instead of kerogen. This is very important at times where source rock material is missing or not known, or you do not know what the source rock is. So this oil asphaltenes can be used as in a kind of a backward modeling approach or in kind of a top-down approach. Also, perhaps for calibrating your predictions you did on the source rocks. In cases, for example, in high maturity fluids where asphaltene contents are low and you cannot precipitate asphaltenes, resins may still yield important source information. And those polar resin compounds can be assessed using high resolution FDIC-RMS spectroscopy and can be performed on all types of petroleum fluids for oil source and oil correlation, and can yield important information on source rock contributions or maturity, expulsion timing, or the extent of fractionation caused by differential migration or migration distance, and also the level of biodegradation. So I don't want to step deeper into this topic, but I would like to announce that we would like to propose a multi-client study called PUPPY, Practical Upstream Petroleomics and Pyrolysis, using this FDIC-RMS and pyrolysis methods for analyzing asphaltenes and resins. Because the technical goal of this project is to use resins and asphaltenes for source rock identification, source rock kinetics, inherent source rock PVT signatures, and tracing expulsion and migration pathways, finding oil families and mixing scenarios, and physical property prediction. And that resins and asphaltenes can be a nice tool in exploration, development, and production. So Brian Horsfield, who is here, he will also give a talk at the Petroleum System Conference on the value of using heavy ends geochemistry and petroleum system evaluation. So, okay, now this shameless announcement was the end so far, and I want to leave you with the take-home message that phase kinetics or gore-fed delivers sound bi-petroleum fluid prediction in a broad variety of petroleum provinces and for low to high maturity plays. So the output can be directly imported into modeling software, and if using a GORFET model, you should deactivate secondary cracking schemes, because the secondary cracking schemes are already in the model. Okay, what you could do is, or what is needed by us to do the job, to construct those phase kinetics and GORFET models, is potential source rock material, 5 grams is enough, or reservoir core, DSTs, oils, shows, or seeps for asphaltene precipitation if we use the asphaltene as an kerogen indicator. Okay, and what we do besides just being great is the modeling, the kinetics modeling approach for PVT prediction, and FT-ICRMS is part of a more fully integrated analytical approach with quick insights on source maturity, expulsion timing, migration, fractionation, etc. And not to forget is, since Alex Hartwig joined us at Geosphere now, is that we also would do the petroleum system modeling itself, using those models, of course. Okay, that's it.
Thank you very much, Nick. Yeah, that was a very nice presentation. Lots of information. I think some of them I have to digest maybe even after. For all the participants, now it's time to either raise your hand or type a question in the chat box. So if you want to raise your hand, at the bottom of your screen there should be a little hand. If you click it, then you can unmute yourself after we name you, and ask your question, or type one in the chat box. Make sure it's for everyone so we can read the question. In the meanwhile, while people do that, I go with my first question. So let's say if I try to paraphrase and maybe dumb it down for my level, let's say the main difference between the GORFET and the traditional ones is really that you try to improve the impact of in-source secondary cracking, and you got the information by basically running an open pyrolysis and get the GORs from that, and then basically adjust or tune your phase kinetics towards these higher instantaneously generated GORs. Maybe it's a little wrong, but on a higher level, is that somehow how?
Yeah, the GOR fit, the GORFET method assesses the source-specific secondary cracking kinetics, and then in the GORFET model, and this source-specific secondary cracking kinetics is integrated into the bulk kinetic scheme. So you do not need to switch on secondary cracking kinetic models, default models in your modeling software, but you just use the complete model. And the GORFET uses one pyrolysis GC run for fitting all the closed system compositional data, but to now really find how much of those secondary cracking potentials should go into the bulk kinetic model, you have to know the expulsion efficiency, and you cannot. I mean, we did kind of, that was a more swag than knowing, but you can use also mass balances for your petroleum system if you know for sure how much is really expelled or retained in the source rock to construct the correct expulsion efficiency and get the correct potentials.
Yeah. Okay. Yeah, thank you for that. We have some questions coming in. I think some of them are maybe for Alex. I think the first one is about basically how good, or basically how do you know that what you do with your kinetics can explain the accumulation properties in the subsurface? Any quantitative measurements for that? And I guess that maybe is a question for one of those case studies, I imagine. but it's up to you guys.
No, I can answer that. I think we do not always know for sure that is always the composition that you will find in the field. So it's a bottom-up approach. But because what we predict is actually the kerogen and the maturity dependent composition. So involving secondary cracking. But now what happens, those secondary physical parameters during phase separation, stuff like that, we cannot really directly model that. Or you do not see that in the model directly. You have to run the model and look what's coming out there and then compare. So we cannot, so it's just the input parameter for the basic input parameter for your source rock. So we cannot know all the effects that will happen on this composition, but we are pretty sure that will be the first produced composition that will start to travel through the carrier reservoir system.
And maybe to add to what Nick has said, so in the case studies, we actually tried to address the question that was asked. So we based on the modeling, we chose certain accumulations where we knew there was only one source, and that they're in a location where migration is where you're, so to say, on the edge of some sort of migration effect. So either you're at the edge of, let's say, the migration envelope, so where where you have to have a kinetic that helps to explain your accumulation, because if your model is too hot, you get a lot of accumulations, even though there are dry wells around. Or if your model or kinetic is too your model is too cool, or your kinetic is too stable, you will not get an accumulation. So it's right on the edge of or very sensitive areas. So we chose several of those and looked at the PVT data that is available, and then said, okay, what type of a source kinetic do you need to produce the accumulation? And then the next step then was to say, well, does that kinetic actually predict the physical properties of the oil that were proven? So that was one of the approaches we used to do this. And for example, for the Draupner formation, if you take 10 Draupner samples, you will get slightly different kinetics for them. Some will be a bit more labile, some will be a bit more stable. So you have to do a bit of a selection. But in the end, once you've gone through that process that we did here in this very mature area, you can really find the one kinetic that works really well to explain all these, let's say, accumulations on the edge of the migration front, but in the end also has the bulk composition to explain the gas that you find in the mature areas. And the key there was that, our goal was to say, well, can we use one kinetic for each source rock interval to use that, instead of mixing different kinetic models? And so that was the challenge. And the proof really comes from the oils themselves and the PVT data to say, okay, yes, that is possible.
Yeah. So I'm just, while we continue answering some questions, I just have that highlight up here for future reference, so people can see what's coming up. I think another question was a bit more general about basically oil retention, right, in the source rock. I mean, how do we know how much is retained in the source rocks? And depends on type and so on. So what are the assumptions there?
Yeah, I mean, in our models now, we did not run those mass balances. Okay, I think I answered that in the question before. You have to run Rocky-Val-based mass balances if you can. Otherwise, you just have to guess. Or if let's say your source rock is very, very aliphatic or paraffinic, then you can assume a very high expulsion efficiency, so not much is left retained in the source rock to be cracked. If you have a very aromatic source rock, or very interconnected source rocks, or heterogeneous source rocks like coals or terrigenous organic matter, then the expulsion efficiency will be rather low, and much more will stay in the source rock environment to be secondarily cracked.
Yeah, I guess first of all, Pep and Corby have published some numbers on that, what they assume exactly. So folds retain most of the liquids, right? That's why they don't get expelled. So you could use rocky wall pyrolysis to establish your own scheme, look at all the unconventionals, get some information from there, how much you retain. Yeah. Okay. Actually, so maybe one more question from my side. So basically, the main observation was there's not enough gas was generated, and so you kind of adjusted that. Do you think that might be the reason why not enough gas was generated was maybe because of this closed system pyrolysis? Some people say like, well, it's the pressure, it's too high, and things like this, and this is why you have to adjust it. Do you think that's part of it? I'm just thinking about it because one of our upcoming talks from Harald Kark will talk about pressure's impact on kinetics. So maybe your thoughts on that quickly.
I think just I think the B-type facies generated too low gas, but the Gore-Fed kinetics generated enough gas to explain all the occurrences. So yeah, you should use those secondary gas cracking schemes in your models. So closed system pyrolysis might explain the missing gas in other places. Yeah.
Yeah, I think one of the challenges was really to have enough gas in some of the systems, and there are different ways of tuning that in a model. But it seems that in this case, secondary cracking is part of the issues, especially if you're in the high mature areas. And that can be adjusted with the Pepper and Corby models, and there are different secondary cracking schemes out there. But the challenge is always, which one do you choose? Do you just run with the default? And I think it will give okay answers. There's no problem with that. It's just if you really want to start pushing the boundaries, and if you're in very mature settings, it turns out you do need to be a bit more specific. In a frontier area, we know very little. So then, general schemes are definitely good enough. But if you're in a mature setting, then those generalized schemes, start to be challenged. And even very specific schemes or models are being challenged as well. So no doubt about that. So it does take time and effort to work through it. But the secondary cracking, the source-specific secondary cracking does play a role.
Okay. So then, thank you very much again to Nick and Alex. Great presentation, lots of information. As we said earlier, I think this session was actually recorded, okay. And we will post it, or we will definitely get something together to make available for everyone. And with that, I just want to highlight September 30th. We have a presentation coming up from Björn Vigralla about geothermal. So I hope you will have the chance to dial in and sign up. And lots of other interesting topics following this and next year. So with that, we are finishing on the minute. Wow. Thanks again to everyone, and hopefully see you all soon again.
Thanks for having me here.
Thank you.
Thank you.